Good day, distinguished participants, researchers, and guests. My name is Anslem Otutu, and I'll be presenting our study titled Explainable Machine Learning Assessment of Land Cover-Driven Environmental Vulnerability in Tower Hamlets, United Kingdom. This work was done in collaboration with Prince Chukwuemeka, and we examined how explainable machine learning can be used to identify environmental vulnerability patterns in urban environment. Introduction. Urban environmental vulnerability is shaped by land cover, built-up density rainfall extremes, terrain and access to natural infrastructure. Dense boroughs such as Tower Hamlet can show sharp spatial contrast over short distance. Remote sensing and machine learning provide a practical way to integrate heterogeneous spatial predators into decision support maps. Sharp-based explainability help identify which variable drive the vulnerability surface. Our aim is to develop a reproducible and explainable machine learning workflow for assessing land cover-driven environmental vulnerability in Tower Hamlets. Generate a rule-based vulnerability index from environmental and urban indicators. Train and compare logistic regression, gradient boosting, random forest, and extra trees model. Map 5 class environmental vulnerability, probability, and confidence surfaces. Explain model decision using feature, importance, and sharp values. Identify key limitation and validation needs for future applied use. Study area, Tower Hamlets, London, United Kingdom. 20 predators represented terrain, land cover, vegetation condition, moisture, rainfall regime, green space, built infrastructure, and geology. The rule-based vulnerability index was used to create a proxy binary target, but the index itself was excluded from predators to reduce direct leakage. Here is a summary of machine learning workflow used in this study. We prepared spatial data by aligning layers, clipping to boroughs, and harmonizing predators. Rule-based index. We developed references, environmental vulnerability surface, proxy target creation, derived binary vulnerability labels while excluding the index from predators to avoid data leakage. Spatial validation, use partial blockage split and grouped cross validation to reduce spatial autocorrelation bias. Model output. This generated 3 outputs: produce probability, 5 class vulnerability, and confidence maps. This map illustrates the rule-based vulnerability surface, which serves as a reference framework for our study. The rule-based index provides the reference surface for auditing target creation. The map shows a broad west to east gradient. Higher index value occur in the western and southwestern sector. Lower values are mainly concentrated towards the eastern side. Machine learning vulnerability classes. The result shows that very high value vulnerability is concentrated mainly in the western and central western parts of Tower Hamlet. Next is probability and confidence surfaces. high predator vulnerability probability are concentrated in the west. Low probability dominates much of the eastern borough. Model confidence is generally high across the map. Transition zones show more mixed confidence and should be interpreted carefully. Model comparison and validation. We compared 4 machine learning algorithms and we found that logistic regression rule provided the best balance between predictive performance and interpretability. Explainable and key drivers. Built infrastructure and rainfall-related variables dominate model behavior. High value of rainfall anomaly, extreme rainfall, and building presence tend to increase predicted vulnerability. Survey and distance to grid space contribute additional environmental context. Discussion and planning implication. The vulnerability pattern is not only a land cover signal, it is also a rainfall infrastructure signal. Building and distance to building indicate that urban fabric and exposure to build-up surfaces are central to map vulnerability. Rainfall anomaly and extreme rainfall shows how climate stressors interact with land cover and infrastructure. High confidence away from transition zones supports screening uses, while boundary areas require more careful local interpretation. Conclusion. The study produced an explainable machine learning workflow for land cover-driven environmental vulnerability mapping in Hamlets. Logistic regression was selected as the best balance and most interpretable model, achieving 0.991 accuracy. Very high vulnerability is concentrated mainly in the western and central western hamlet. Key drivers are buildings, rainfall anomaly, extreme rainfall slope, maximum daily rainfall, and distance to buildings. Main limitation. The target is proxy derived. Stronger feature work would use independent observer outcome data. Thank you for your attention and your interest in this research. Questions?